Okay, so let's go ahead and find a formula for the sum of the diagonals in an n-sided polygon today. Okay, so we're going to use kind of a reverse mathematical induction technique to determine the number of diagonals. Okay, so we can describe a pattern developing. So if we have three sides here, clearly we have 0 diagonals. Okay. All right. And if we have 4 sides, okay, 4 sides, we're going to have, let's count them up. So we're going to have 1, 2 diagonals. Okay, so 4 sides, 2 diagonals. Okay. All right, now if we have 5 sides, this is a pentagon, so let's do our best to sketch that. Okay. Doesn't have to be regular. Again, it can be any pentagon here. All right. So let's count them up. So if we've got 5 sides, we're going to have 1, 2. Okay, exhausted that. 3, 4. Okay, exhausted that. And 5. All right, so 5 sides, 5 diagonals. Okay. Very good. So now let's think about a 6-sided polygon, and then we'll maybe do 7-sided, and then we'll be probably good to go at that point. Okay, so 6-sided here. Right, so 6 sides. How many diagonals do we have now? Well, let's count them up. 1, 2, 3. Okay, exhausted that. 4, 5, 6. Exhausted that. 7, 8. Okay, exhausted that. 9. All right, so 6 sides, 9 diagonals. Okay. All right, let's now consider a heptagon. Okay, heptagon. It doesn't have to be regular, just any heptagon will do. Okay. Okay, so if we've got 1, 2, 3, 4, 5, 6, 7 sides, we're going to have here 1, 2, 3, 4. Okay, exhausted that. Okay, 5, 6, 7, 8. Okay, exhausted that. 9, 10, 11. Okay, exhausted that. 12, 13. Okay, exhausted that. And 14. And that's it. Okay. All right. Good. So we've got 5 sets of data, and this is definitely going to be enough to describe a pattern developing. So let's maybe put together a little table here. Okay, a little table of data, so we can organize things. Okay, so this will be n for sides and s sub n for the sum of the diagonals within sides. So if we got 3 sides, we've got 0, diagonals. If we have 4 sides, we have 2 diagonals. If we got 5 sides, 5 diagonals. If 6 sides, 9 diagonals. And if 7 sides, 14 diagonals. Okay. Good. All right, so to get to 2 from 0, we got to add 2. To get to 5 from 2, we have to add 3. Here we add 4. Here we add 5. So we don't have a constant first difference, so we don't have an arithmetic growth pattern. But as you can see, we do have a constant second difference. Okay? And a constant second difference means a quadratic relationship is present. So a constant second difference means a quadratic relationship. Okay. And a general quadratic is going to look like this. So S of n equals an squared plus bn plus c. Of course, let's be clear. We're not talking about a continuous function here. We're talking about a discrete function. So n must belong to the set of positive integers. Okay. Let's maybe zoom out one more step. Okay, so we have A, B, and C as unknown, so we're going to need 3 sets of data. Okay, if I plug in 3, I should get out 0. So let's do that. So A times 3 squared plus B times 3 plus C should equal 0. If I plug in 4, I should get out 2. So A times 4 squared plus B times 4 plus C is equal to 2. And if I plug in 5, I should get out 5. Okay, so A times 5 squared plus B times 5 plus C is equal to 5. So this is the system that, if I solve, should allow me to determine this explicit pattern and formula, therefore, for the sum of the diagonals of an n-sided polygon. Okay. Now, I could, of course, offer additional equations, but it would be redundant. Again, the number of unknowns needs to be equal to the number of equations to find one unique solution. Of course, I'm looking for one unique solution so that I know I have a reliable, consistent formula with definitive values A, B, and C. Right, so let's go ahead and simplify this. It's going to give us 9a plus 3b plus c equals 0. Okay, here we're going to have 16a plus 4b plus c is equal to 2. Here we're going to have 25a plus 5b plus c is equal to 5. Okay? All right. Let's go ahead and solve for c for everything. There are a number of ways we can solve this system. We could use Cramer's rule. We could use the Gauss-Jordan elementary row operations from linear algebra. I do think that since we have c here, we can just solve each one for c and then set c equal to c equal to c, thereby reducing a 3 by 3 to a 2 by 2. Making our lives a lot easier in the process. Okay, so let's solve each of these for c. Okay, so c for the top equation is going to be equal to negative 9a minus 3b. Okay, good. Middle equation, c is going to be equal to 2 minus 16a minus 4b. Okay, and lower equation, c is going to be equal to 5 minus 25a minus 5b. Okay, quickly checking that, making sure we haven't committed any careless mistakes. No, we have not. So now, let's set the top C equal to the middle C, and then let's let the middle C equal the bottom C, and then we will thereby reduce to a 2 by 2, eliminating the need to even consider C. So, setting the top equal to the middle equation, we're going to have negative 9a minus 3b is equal to 2 minus 16a minus 4b. Okay, and then setting the middle equal to the bottom, we're going to have 2 minus 16a minus 4b is equal to 5 minus 25a minus 5b. All right. Let's confirm that we haven't committed any careless mistakes up to this point. No, we have not. Okay, let's go ahead and solve. Let's go ahead and solve both for b, actually, because I can add 4b to both sides and solve for b, add 5b down here, solve for b. Okay, so top equation, adding 4b to both sides, I'm going to have b equals, it's going to be 2, and then adding 9a, it's going to be minus 7a here. Okay, very good. Now for the bottom equation, adding 5b to both sides, negative 4b plus 5b is b, and then subtracting 2 from both sides, 5 minus 2 is 3, adding 16a to both sides, negative 25a plus 16a is negative 9a. Okay. Checking that over ever so briefly. Yes, that looks good. Okay, well, b is equal to b after all. This is actually quite convenient. So we can write 2 minus 7a is equal to 3 minus 9a. And adding 9a to both sides, subtracting 2 from both sides, we can see clearly that a equals 1/2. Okay. Good. So let's go ahead and find b now that we know a. So b is going to be equal to 2 minus 7 times a, which is, of course, 1/2. That is 2 minus 7/2. 2, of course, is the same thing as 4/2, and 4/2 minus 7/2 is negative 3/2. Okay. Very good. Now let's find c. Okay. So we can use this, any of these, but I'm going to go ahead and use this top one. It looks less complicated, or the least complicated, I should say. So we're going to have c equals negative 9a, which is 1/2, minus 3b, which is negative 3/2. Okay, good. So it's going to give us negative 9/2 and then plus 9/2. So well, look at that. C is equal to 0. Therefore, okay, S of n is equal to, we've got 1/2 n squared, okay, minus 3/2 n. And if we want, we can go ahead and factor an n out up on top. And we can also factor out a 2 down here in the denominator. There you go, the formula for the sum of the number of diagonals in an n-sided polygon. Hopefully you found that video to be instructive. Okay, it's important that we understand not only how mathematics works, like, memorizing formulae, but why mathematics works. Now you know why this works. Let me know if you have any questions, comments, and concerns. We are always receptive to recommendations for future content, so please do not hesitate to leave a comment, or a recommendation rather. Have a great rest of your day, and we will see you in the next video.